Welcome everybody. This is Network Science, and in today's lecture, we are going to start to discuss this huge topic, which is called measures and metrics, and this is the chapter 7 of Mark Newman's book. So that's the book from which we are studying. Um, okay, so well, actually, we can also call this as centralities or centrality measures. So, to start with, we can claim that this is one of the most important concepts in network science, and that's so. The basic question is, which are the most important vertices in the network? So you can imagine that. This is a quite general question, and it's I mean, as such, it's maybe impossible to answer it properly, because then one can immediately question back that with respect to what. So like importance with respect to what. Now anyway, we can still say that what we are looking for in general is basically a function which we might want to denote as C, as a centrality. And yeah, so it takes the nodes of the network, but I would put here down VG, because it not only takes the nodes, but apparently it, of course, needs to consider the entire network, so including also the edges. But anyway, what it does, it assigns in general a real number to each and every node. Okay, but of course, it takes into account also the edges. And so in many cases, this part, so the assigned number, in many cases is um, it's a natural number, starting from 0, 1, 2, 3, 4, and so on. But in many other cases, it's a positive or non-negative. Maybe it's better to say non-negative real number. But apparently, there are some centrality measures which does make sense. Of course, they do make sense, and they assign any kind of real number. Well, in particularly numbers between -1 and 1. So negative numbers um, can also be used here, and sometimes they don't really make sense, or maybe they unnaturally make things more complicated. But in some other cases, they definitely make sense. We can maybe have some examples later on. So for sure, we have lots of definitions, and we can start already with maybe the simplest one, which is the degree centrality. And that is such a function which takes again the nodes, and then the nodes, and then they it assigns maybe this is not a proper notation here. But what I would like to communicate is that the degree centrality just calculates the degree of the nodes, and then it assigns the degree. And here on this small figure, this is an interesting example. Interesting because you can see that there are two nodes here, A and B, and the degree of A is equal to 2, and the degree of B is also equal to 2. So with respect to their degree, they are actually similar. So they are similar. I can't say it differently. So they cannot be distinguished from the degree point of view. But on the other hand, you can see it very clearly that B, in some other respect, it plays a big role, because if we remove it, then the whole network splits into two halves, in which both parts actually contains significant amount of nodes. Now, of course, one can argue that if we don't we don't remove it, I mean, we don't remove the node B, but we remove node A, then the network also gets split into two halves. But that's not really, expressive splitting, or useful splitting, because here we have only one node alone, which, well, compared to the size of the other part, is again negligible. So so we can maybe we can maybe say that node B has, in some sense, node B is more important than node A. At least we can have this kind of feeling. Okay, now, sorry about the coughing. Um, so now the next one, the next, or maybe the first, well, the second centrality measure, apart, so after the degree centrality, which we can consider, and it's definitely different from the degree centrality, is the so-called eigenvector centrality. Now, for for eigenvector centrality, maybe it's worth to, do a certain rehearsal, which is that, if we have a matrix A, then the so-called eigenvalue problem is that we are looking for the solution of this system of linear equations, where vector x is not a zero vector. Okay, and so A is a known matrix, but x and y sorry, x and lambda, they are unknowns. So x, if we find such an x which fulfills this equation, then x is called eigenvector of A, and lambda, which is a number, is called eigenvalue of A. So apparently they can be even complex numbers, complex in general. Okay, and well, there are, so I mean, if the matrix A is of dimension n times n, then we have n eigenvector or eigenvalue and n corresponding eigenvectors, eigenvectors. Okay, I mean, Sometimes these eigenvalues, they can be so some of them, so like there could be multiplicity here, so not necessarily different. So these n eigenvalue and n eigenvector, they are not necessarily different. Okay, but in general we have the number of them is always n. Okay, so taking the largest lambda in absolute value, so in absolute sense, uh, we get the so-called dominant eigenvalue and the dominant eigenvector. Okay, and so here in network science we are looking for this dominant eigenvalue and the dominant eigenvector. That's going to be important. Okay, so and the meaning in the context of network science is again the importance of a vertex, and the some kind of background motivation is that we are interested to see whether a vertex gets its importance increased. In which way? Well, it can improve or increase its importance if it gets connected to other vertices which are themselves important. So this is actually a nice recurrent definition, which seemingly impossible to resolve, because it means basically that I am important if I'm connected to important people, and they are important if they are connected to important people, and so on and so forth. So it should be spread throughout the entire network. And so how can we resolve this? Well, we can do it in such a way that well, iteratively we calculate the followings. So we first form a vector which contains all ones. Okay. So in the first step, in step 1, we assign or step 0 or 1, whatever, we assign um, ones to number 1 to each and every node in the network. And then what we do is that we calculate the first vector. So this should be, so x, I mean, yeah, sorry about that. So x 0 should be 1, 1, and so on, 1. So the vector which contains all ones. And then maybe here I should write 0. Okay, so then what we do is that we multiply. So to get the first vector, element I in the first vector, we take the adjacency matrix A, and then we multiply it with these all ones, vector with containing only ones. Okay, and so that means that well, that's just simply, so this what's written here is simply can be written in matrix vector format. So it's simply just a multiplication of our adjacency matrix with vector x. And well, what we do then is that we keep on iterating this equation. Okay, so then of course then x2 is calculated with as a times x1. Okay, but of course, and well, of course, a times x1 was calculated with a times x0. Okay, so now you can see that why we were writing here xt is equal to, changing the notation anyway, so don't worry about it. I hope you understand. So the teeth iteration, the result in the teeth iteration, it can be obtained as the agency matrix raised to the power t, so multiplied with itself t times, and finally we multiply it with x0. So that is the vector of all ones. Okay, so that can be an iteration. Now, if we um, if we take some things from linear algebra, then um, we can have the following. Okay, so apparently it turns out due to linear algebra, vector x0, which is just a vector of ones, it apparently can be written as a linear combination of the eigenvectors, which we can denote as v1 and so on vn of the adjacency matrix A. Okay, that's a fact from linear algebra. All right. So of course we at this moment we don't know. So this is now just theory. Okay, because right now we don't know what are these vectors, right? But the theory says that if we knew it, then so all the vectors can be actually calculated as a linear combination of these eigenvectors. Okay, so you can see it written here. So the linear combination means that we take the vectors v1 and so on vn, we multiply it with some constants, and then we add them. Okay, and as a result we get x0. So what does this mean? Well, it means that we had this equation. Let me change my pen. So we had this equation a times, oh sorry, I should write x t equal to a to the power of t x0. Okay, so we start from there. And now you see xt equal to a to the power of t, and now we take this expression here and we substitute it here. Okay, so that's what we get. Now actually this is now a nice so for all these vi's it holds. So now this step here, it's coming from the fact that that this is an eigenvector in equation, so it holds for each v. So vi, it holds that we have, it's equal to kappa I times vi. Okay, so well, note that I again forgot. So traditionally the eigenvalues are denoted with lambda, but in this book from which we are studying is denoted with kappa. Okay, so kappa now is lambda. And so now this is true because we know that v is an eigenvector, vi is an eigenvector of our adjacency matrix. So what's happening here is that this a to the power of t is, well, I mean, you can see it that it's substituted basically with kappa to the power of t. Okay. So how can I do this? Yeah. So well, I mean, I don't really need to. I guess I don't really need to explain it, but you can see it yourself, right? That it can be basically substituted, the a to the power of t with kappa I to the power of t. Okay, and then we need to, of course, take it into the sum. And now we can even take out the first eigenvalue. So let's assume that kappa 1 is the largest eigenvalue. Okay, then if we take out from the sum, then we need to, of course, to the power of t, we need to, of course, divide with it to get the equation. But from here, what we can really see is that given the fact that kappa 1 is the biggest one, so then this guy here, so what we have inside the brackets, now that one is, so I mean, this is, how should I write it? So that one is smaller than 1. Okay? And because it's smaller than 1, if we take t to infinity, then the thing in the bracket is going to be converging. And actually, it's converging to this expression here. Okay, in which you can see that what is left is the first one. I mean, now you can see that I mean, this is a sum, right? So it's a sum, and I is still here as an index, which goes from 1 to n. So then this one, I mean, converge. I forgot to say that that this thing, because it's less than 1. Then if t goes to infinity, then all these terms they are going to be 0. So they are converging to 0, except one, which is the case when when I is equal to 1, because then it's just this quotient is equal to 1, right? Because kappa 1 divided by kappa 1. So all the left, all the other terms of this sum, they go to 0 in case t goes to infinity. So what remains is c1 times kappa 1 to the power of t times v1. And so what we can see is that the limiting vector, so our vector which we are looking for, is proportional to the leading eigenvector of the adjacency matrix A. Okay, so so that is the thing which we are looking for, the leading eigenvector, or, well, in this note here I was calling it dominant eigenvector. Okay, so that's these are two expressions for the same thing. Okay, so let's see. So what does this mean? It means that the eigenvector centrality can really be calculated by simply considering this kind of eigenvector problem, in which we need to calculate only one eigenvector and one eigenvalue, which is the dominant eigenvector. Okay, and that's the thing how this can be calculated. And well, given the fact that we were considering only non-negative numbers in the calculation, so a at this moment it can have only zeros and ones, and if the network is weighted, then it can have positive numbers or non-negative numbers. Then what we obtain as an eigenvector centrality, all of them are non-negative numbers. Okay, now, well, here is an illustration, and you can see now that the coloring is such that if we have for this particular network, which is taken from Wikipedia, if the network, if the eigenvector centrality value is high, then the color is red. If the eigenvector centrality is low, then the color is blue, and we have some yellow and green nodes as well, so they are somewhere in the middle. Okay, and what is interesting to see here is that you can see it already that the coloring would be completely different if we were coloring according to the degree centrality, because now you can see that, for example, here at this part we have some nodes with relatively low degree, which we have also here, let's say, or here to the other side of the network. And so they are somehow, this part on the right, they are somehow far away from the central nodes, from the most important nodes, and so they are not connected to the most important nodes, and hence their eigenvector centrality is low. Okay, so it's I mean, if we if it well, I'm not able to remove now the coloring because this is of course a PDF file, but if I removed the coloring, it wouldn't be, I mean, maybe the coloring for the degree centrality would be relatively easy to do, but the coloring for the eigenvector centrality might not be easy to find out, right? So in that we should agree. Okay, so I think this is the end of the first video of today's lecture, so we continue in the next one.